Welcome back, gangies. It's dumb late. It's 1:30 a.m. We made some bad decisions. We didn't do the LC as early as we planned to, as usual, which has left us screwed. And with only one option remaining, to do it at 1:30 a.m. So it's kind of where we're at. Work has been crazy recently. Also, Gartic Phone is a pretty cool game. It's pretty epic. This is where we're at. Yeah, I would say this is where we're at. We're stuck on foursome, which is depressing. I don't think we have any comments, so we have no choice but to accept our fate. And it's not possible for us to stall this time around. Let me double check. Yes, we have no comments. The HCC has abandoned me, but fortunately, neither time nor tide wait for man. So we were in this alone to begin with. I actually don't mind doing this session, but what is going to bother me is not having finished this problem. And I'm also relatively certain that we're not going to solve it. I think we'll solve it this weekend. The problem is, I feel like with some of these problems, there's an amount of time you have to think consecutively to make stable progress, and 30 minutes just isn't enough time. By the time I get to 30 minutes or 20 minutes, which is probably what we're gonna do, is when I'm just finally resaturating with all the attempts I've tried, and then it's starting to make sense. So by the time we get to the end of the time limit, it's really when we should be starting. So I feel like an hour to 2 hours is really the ideal thinking time. So I think tomorrow maybe we'll set a timer for 2 hours and see if we can dunk on it, but who knows, honestly. That being the case, we are back. So yeah, things are looking up. I have a really good feeling about this year. So hopefully things will stay interesting. Enough ominous speaking. We're about 3 minutes in. I'm going to set a timer for about 20 minutes. And I'm just going to pray to the dear hyperbolic coding gods to bless us with a way through. But I think it's a good idea that we stay on these problems until we can actually make some progress. So I refuse to look at the solution unless it's some kind of math. Unless you're doing a problem where the cheat code is like, there's a problem where it's pretty much impossible to solve. The only way to solve it is to use some secret cheat code some Latin mathematician figured out in 1750. And it's like, what are the companies testing there? Either you fail the question, either the candidate fails the question, or the candidate is Aristophanes himself. So it doesn't make any sense. Either way, something's just funny about the answer just being literally something a 1700s mathematician figured out in his basement. Either way, I'm going to restart the timer since we already burned some time. I'm pretty much trying to solve foursome using a modified quantum time solution. This runs for the first case. Oh, it fails for negative numbers. I remember now. Yeah, so I wonder if our style is fundamentally flawed. We added some code to be able to switch the goal based on what we're searching for, but let's just say our target is indeed a negative number. If we, oh no, oh my God, we don't actually have to, I think we can actually remove all of this nonsense. If we remove these 4 cases we added of absolute nonsense jargon, the cheat code I think is actually pretty simple. If target is less than 0, I'll say less than or equal to 0, we'll sort in ascending order. Else we'll sort in descending order. Okay, we're passing even less cases, which is crazy. Which is interesting because it shouldn't have changed anything. I think we have to remove target pos. I have a really good feeling about this. Okay, maybe we're delusional. For some reason, this is sorted in. Something is definitely wrong here. Yeah, I have it swapped. It should be like this. This actually performs worse. When we sort it in descending order instead, our goal is negative, so if we sort it in reverse, so that style was nonsensical. Oh my God. This doesn't make any sense. The hints are 2-pointer and sorting, but it's unclear how sorting helps. Why would sorting help us find numbers, 4 numbers that add up to a particular value. Let's just say a target is 5. If we have a negative 10, if we have 2 zeros, a negative 5, a negative 10, and a positive 10, if you sort those values, let's just say negative 10 and positive 10 are the minimum and maximum. They would be at 2 opposite sides of the array. So how does sorting help? This really don't be making sense for real. Sorting up, sorting down. 4-pointer approach with heuristic. 4-pointer is not even an actual thing. 3-pointer is a thing. What if you did 2 sets of 2 pointers? Wait a second, that might actually... Oh my god, that might actually be bonkies enough to work. What if we did 2 sets of 2 pointers on a sorted array like we mentioned up here? We sort the array, and then we would do, a for loop over this. So we'd take, with I not equaling j, we'd try -2 and -1, right? Then, since it's sorted, we could take the second half of the array and then move it up and down to see if we can actually find the target. How would this let us cut through the cruft? Well, for each element, we would do n operations. Actually, what's nutty about that is it doesn't include 4 pairs that would be included in half of the array. Or I guess it always assumes the 4 pairs will be in opposite sides of the in the second half of the array. So what is actually the play there? I don't know. I don't know. Life truly do be being crazy though. That doesn't work because the one half of the array would not be in the same half of the other one. Doesn't make any sense. Maybe we could fuse them. If we take 2 numbers, wait a second. What if we did do that? What if we did do We did an n squared loop to consider two numbers, and then since the array is sorted, one, we can stop once our base number is larger than our, no, we don't, because we don't know. But we could skip I and K, I and J, and then increment up or down to know if we can actually add up to it. And we'll basically stop. That would do n squared It wouldn't be exhaustive though, so that doesn't even make any sense. I don't see how you get through this without some method that is exhaustive. You can't two-pointer this. How can you two-pointer this? What if we change how we think? How can we two-pointer this in an exhaustive way? What if we did n squared operations to load all the two pairs into an array? Then we can load all those numbers into a map. If we load all those numbers into a map, then we can iterate over them and ask if the complement exists. That would be another n squared operation. And I feel like that makes sense. What was the problem there? The problem there is there could be multiple numbers that sum up to something. If there's multiple numbers that sum up to something, then it's possible we could have multiple sums. So you can't ever really have a mapping of 1 to 1. I'm pretty sure that's essentially what our first solution did. The problem is we have to check every I feel like we're going in circles on this one. 4, 4, 4, 4. Four-pointer approach with heuristic, brute force optimization, and script version plus two-pointer. I don't understand. I guess that's the point. I think tomorrow we'll be able to solve this. I think we need a longer thinking session. It's not 20 minutes. It's like I feel now like I'm ready to think for an hour, but it's 2 a.m. If I think for an hour, it's gonna be hard to sleep after. There's got to be a small optimization we can add on top of the original time limit exceeded version. I actually think we can check this one here. We got TLE on this one. If I submit this one, Okay, so we got TLE. If instead of this second for loop, we just look it up in the map, could shave some time down. The problem though is that the problem is that what is the parabola? Even if you load the whole thing into a map, more than one number can map to an indice. Wait a second. We get TLE here. What's the input? Wait a second. If we go back to our... Wait a second. I think I just had a brain blast. If we go back to our original one here, and you run it, what it fails on is like the last four. Yeah, it fails on like the last 5 cases. But a lot of these numbers are very similar. So I hate to say, we probably have a lot of duplicates. If it has the complement, then we choose to do some work we get all the complement indices, and then for all the sum indices, all the ones that sum up to, let's just say 20, are going to be in here. Which means we have to do like a dot product of all of those times the complement indices. There's got to be a way to filter out some of the nonsense here. You can have multiple no. It says A, B, C, and D are distinct. They mean the indexes, though. I don't understand. I don't. It feels like the most the better way. I'm only 5 edge cases off. We should be able to sneak past this. My problem is, how many 180s are we going to check? If we check every... Well, we only do the double for loop if we actually have a complement. I wonder what the actual number is, though. Oh, we do a lot of double processing. Actually, I don't understand why that's happening. Target here is 0. We have 6 combinations that sum to 1, 6 that sum to -1. So we do see that there's some double processing here. We have 1, -1, and then we end up working with -1 and 1. The reality is, after we've processed a sum, we've processed all possible combinations for it. So we can say sum set equals new set of type number. And if the paired map has the complement and sum set does not have sum, then we'll do sum set dot add sum. And I think this should help prevent the double processing. I'll remove the console.log so we can make it through the time. Still, I'm not gonna lie, this is actually kind of crazy. Now that I'm checking, are we making sure we're not doubling up on complement indices? Because the sum set thing might have been nonsensical. Maybe we can reduce the total number of indices compared. What doesn't make sense to me is that how are there 380 ways to make 20? Something's wrong here. Okay, it actually does make sense. Because we pretty much do n squared here, and then we add the 1920s in this row, and you get 380 ways. Seems like the problem is now there ends up being a ridiculous number of ways to handle all this nonsense. Because if you run it, there's 380 ways to make 20, and then 3,800 ways to make. Ugh, I'm dumb tired. I think we'll stop there for today.